In section 6.8, we look at the use of electron orbital diagrams to show how electrons are spinning within orbitals. So electron configurations describe how many electrons are in every subshell. So if I look at this electron configuration here, what it's really telling me is that I have 2 electrons in a 1s subshell. That's what the 2 there is saying. Then I have another 2 electrons in a 2s subshell. And then finally, I have 4 electrons in a 2p subshell. So, that's great and all, but it's important to realize that some subshells have more than one orbital per shell and per subshell. And what might be interesting to know is that how are these electrons distributed amongst these different orbitals that make up a given subshell. Now, for an s subshell, there's only one orbital. But for p subshells, we get 3 orbitals. For d subshells, we get 5. And for f, we get 7. So orbital diagrams are what we're going to use to show how the electrons are arranged in the orbitals. And there's really 2 things to keep in mind. We're going to use the Aufbau principle, which is exactly the same as what we were using for electron configurations. We just use the Aufbau diagram. But then we're going to use this thing called Hund's rule. And Hund's rule describes how the electrons organize themselves within different subshells. So, within different orbitals, So what we need to keep in mind is that we need to know the Aufbau diagram, or at least have a copy of it at hand. And then we need to know the number of orbitals that are in each kind of subshell. And as I mentioned previously, an S subshell has 1 orbital, a P subshell has 3 orbitals, a D subshell has 5 orbitals, and an F subshell has 7 orbitals. And often we'll indicate the subshells in an orbital by drawing one dashed line for every orbital. Sometimes people will draw boxes. That's okay. It's kind of a bit of work. Sometimes people will draw circles. I don't really like the circles thing myself. I just find it a little awkward. I normally go with one line for every orbital. So Hund's rule is a new rule that we need to recall, and it says that electrons will not join electrons in the same orbital if an unoccupied orbital of the same energy is available. Electrons in the same orbital have opposite spins. So what we're really saying is that we won't pair up in an orbital while we have another orbital vacant, if that orbital is another orbital of the same energy vacant. So it's kind of like seats on the bus. People tend not to sit next to strangers if there's an empty seat that they can sit by themselves. So this is the correct arrangement for putting 3 electrons into a p subshell. This is the incorrect arrangement for putting 3 electrons in a p subshell. Now something to keep in mind is this last bit here. It says electrons that do go into the same orbital have opposite spins. So if I was to put a 4th electron into this p subshell, I would go back and put it in with the spin down. A 5th one, spin down. A 6th one, spin down. By convention, the first electron goes in, spin up, and then the second one, if we do add a second one, goes in, spin down. So in an electron orbital diagram, the electrons are indicated by either upwards or downwards directed arrows. They're normally these half-headed arrows. And then we put them in either labeled boxes or circles, or like I said, people generally just put a line. So we can go through and have a look at a few of these orbital diagrams and some of the terms that we're going to use to describe them. So writing out the orbital diagram for hydrogen. So hydrogen has 1 electron and its electron configuration is 1s1. It's important not to confuse electron configuration with orbital diagram. So we draw 1 box for every orbital. So a S subshell only has 1 orbital. So we just got the 1 box. We've only got 1 electron to put in it. So there is that. Your orbitals do need to be labeled with the name of the orbital. And this is an orbital diagram, and you can see it looks completely different from the electron configuration. One of the terms that we'll have to get used to is we will be talking about unpaired electrons. And an unpaired electron is simply an electron that is in an orbital by itself. It doesn't have a partner. Okay, so moving on to helium. Helium has electron configuration 1s2, and S subshell has only the one orbital, so its orbital diagram looks like this. It's just a single orbital there. We label it, and we have to put 1, 2 electrons in. The first one goes spin up, the second one goes down, spin down. When we have 2 electrons in the same orbital, we describe those electrons as being paired. So now we'll move on to lithium. Lithium has 3 electrons. It has the electron configuration 1s2, 2s1. The 1s subshell is comprised of one orbital, and it has 2 electrons in it, one up, one down. The 2s subshell is also comprised of one orbital, but it only has 1 electron in it. So this guy's got 1 unpaired electron and 2 paired electrons. Beryllium is element number 4, so that means it's got 4 electrons, 1s2, 2s2. It's got a helium core, and then the outer electrons are these 2s electrons. A 1s subshell is comprised of one orbital, and it's got 2 electrons in it, one up, one down. And then the 2s subshell is comprised also of one orbital, so 1 electron up, 1 electron down. So this atom here has no unpaired electrons. Atoms that have no unpaired electrons, they are described as being diamagnetic. Okay, boron is element number 5, has electron configuration 1s2, 2s2, 2p1. Again, you can write the condensed or abbreviated electron configuration. It's got a helium core, 2 electrons in the helium core, and then it's got the remaining 3 outer electrons. So 1s2, the 1s subshell just has one orbital. 2s2, the 2s subshell just has the one orbital, and then now the 2p, and you can see we've drawn out 3 orbitals here. We only put the 1 electron into the 2p subshell, so it goes in spin up. Carbon, atomic number 6, so it has 6 electrons, 1s2, 2s2, 2p2 is its electron configuration. The 1s subshell has 1 orbital, it's got 2 electrons in it. The 2s subshell has 1 orbital, it's got 2 electrons in it. The 2p subshell, like any p subshell, has 1, 2, 3 orbitals, and now we want to put 2 electrons in there. So one goes in spin up, second one goes in spin up. So if you have multiple unpaired electrons, you're always going to put them in spin up. Okay. Nitrogen, atomic number 7, so that means it's got 7 electrons, 1s2, 2s2, 2p3. So 1s has 1 orbital, 2s has also 1 orbital, 1s1, 1s2, 2s1, 2s2. And then we get to the 2p. So the 2p subshell is comprised of 3 orbitals. And then we go 1 electron, 2 electron, 3 electrons. So we've got multiple unpaired electrons. So atoms that have 1 or more unpaired electrons, they're described not as diamagnetic, but as paramagnetic. So we've got a few terms there, diamagnetic, paramagnetic, unpaired electrons, and paired electrons. You need to know the names of those terms. Okay, so when we move on to oxygen, 1s2, 2s2, 2p4, 8 electrons because it has atomic number 8. So there's the 1s, the 2s look just the same. Now when we get to the 2p, we've got our 3 orbitals. We go p1, p2, p3, and then we go back and start pairing up. So p4, still paramagnetic because we've got 2 unpaired electrons. Fluorine, atomic number 9, so we've got 9 electrons. It's 1s2, 2s2, 2p5. The 1s still looks like what it always has. The 2s is completely full, and then here we are into the 2p. We start doubling up in our second orbital now. We've only got the 1 unpaired electron, still paramagnetic though. Okay, after fluorine comes neon. Neon's atomic number 10, that means it's got 10 electrons, 1s2, 2s2, 2p6. Completely full 2p subshell, completely full 2s, completely full 1s. So all of the orbitals are doubly occupied. The 1s just has 1 orbital, the 2s has the 1 orbital, the 2p, just like any other p subshell, is made up of 3 orbitals, everything is completely paired up. This guy is going to be diamagnetic, and it has 0 unpaired electrons. Okay, so that's how electron orbital diagrams work. So the arrangement of electrons in orbitals can be shown using an orbital diagram. There are 2 rules that we follow. We follow the Aufbau principle, just like we did for an electron configuration, but we also follow Hund's rule, where we don't pair up electrons in orbitals of the same energy until every orbital in that subshell has at least 1 electron in it. We define the terms unpaired electrons, paired electrons, paramagnetic atoms, and diamagnetic atoms. It's important to recognize that paramagnetic atoms are attracted to magnets, whereas diamagnetic atoms are not.